mixins express optional or orthogonal behavior. So orthogonal basically means supporting behavior that might be useful for you. And there are lots of examples of mixins within the Java library. So for example, instances of a class, they might implement, any class can implement their primary behavior, like a student can implement person, but you can also implement serializable if you want. Okay? And if you implement serializable, that means that your class now can be serialized into a byte stream, and you can transfer your data over the internet, for example. So if you want to do that, then you have to implement serializable. Another thing, if you want to be able to use the clone method from the object class, then you need to implement clonable. So another one is comparable as well. If you want to be able to make use of the compare method within the comparable interface, compare between two objects to see if one of them is greater than the other. So you acquire additional behavior. Special interfaces like serializable or clonable are what we call markers. There's no additional methods that you need to implement. So for example, if you implement the serializable interface has no methods. Okay, you're just telling anybody that's using your class it can be transferred into a byte stream to be transferred. Also the clonable interface has no method. You're just making use of the clone method that exists within the object class. So marker interfaces have no methods but declare a type. So essentially some capability that implementations support. So let's say we want to create a create a class that does something, and this something is some kinds of statistics. So one thing that banks want to do a lot is they want to do statistics on the money that's in all the different accounts of all their customers. So let's say I want to implement a calculator that performs calculations over instances of different classes. So for example, the accounts of our bank account example, and let's say we've got another class, something nothing to do with banks at all, cash box. So in a supermarket, for example. So let's say a supermarket, there's a number of tills, and you want to perform calculations, which till has got the most money, which till has got the least money, what's the running total of all the tills, how much money has the supermarket made in today. Both account and cash box concern money. We want to create a calculator that calculates statistics over instances of either of those types. So these obviously are not the same, they're different. You put money and remove money from them in a different way. And let's say supermarket, in order to have these statistics, they would need to create their own statistics class, and the bank would also need to create their own statistics class. So let's have a look at those implementations. So we'll first implement calculators specific to accounts and cash box. Then we'll show how to use a mixing interface to provide a more general calculator that anybody can use. So anybody like a supermarket, like a bank, like I don't know, the stock market, anybody that wants to have these general statistic calculators. But first we'll look at the specific calculators created for those individual classes. So let's have a look at the cash box class first of all. So cash box is a lot simpler than the account. So then the accounts, we had an abstract account, we have an overdraft account, and we have a free account. Cash box is just a cash box. There's no interface. It's just a simple class. I've got an amount of cash within the cash box. I've got a constructor. Well, I've got two constructors actually. So one constructor doesn't initialize anything, and the other one does initialize. So you initialize the amount of money within the cash box. And we've got a number of useful methods. So we've got total here, returns the amount of money within the cash box. Empties the box and returns any cash within the box. Okay. You can pay into a cash box. So you've got two pays. One if you're paying the amount expected, the exact amount, and one if you're not paying the exact amount, so you'll have to, and returns the change when you're paying the exact amount. Okay, so it doesn't really matter what methods are. So we're just having a general look at what methods you could have within such a class. And obviously, so this is just just a reminder here to have a toString method for most of your classes. So this just returns a string representation of how much cache is within the cache box. So that's the cache box class, and I want to have a calculator on all cache boxes. And what I'm looking at mainly is I'm looking at the total amount that exists within the cache box, and I want to perform various statistics on those on the cache boxes. So, for example, I've got a supermarket. As I said, I've got a number of cache boxes. I want to calculate the running total. So I want to work out how much cache is in all the cache boxes put together. I want to work out which cache box has got the maximum amount, which cache box has got the minimum amount of cache. So in order to do that, I've got an update method. And what the update method does is actually pass into it each of the cache boxes. So maybe you'll run this within a loop. You have like a for loop that goes through all the cache boxes, and one by one you pass into it all of the cache boxes one by one. We've got our running total here, again, is equal to the running total plus the running total plus whatever the box has been passed in, okay? And then I want to figure out which box has got the minimum value and which box is the maximum value. So first of all, we're checking that this is not the first time I'm doing this calculation. If it's the first time I'm checking it, then it's basically the max value and the minimum value will be null, okay? In that case, the max value is equal to this box, and the minimum value will also be this box, because it's the first time I'm doing it, so it's obviously that. On the other hand, if it's not the first time that I'm doing this check, then we check if we compare my current max value with the value of the box. So I say if the max value total is less than the box total, then the max value is equal to the box. And if the min value total is greater than the box total, then the min value is equal to the box. And this way, these two variables here keep track of which box has the maximum value and which box has the minimum value. So that's simple enough, yeah. So these are the statistics we want to. Obviously, a calculator class will be much more complicated than this, but we just want to show a simple example. So we're just maintaining the running total, which box has the minimum value, which box has the maximum value. And notice that the key thing that we're using to calculate these values is the box total. So that's a method. So that's this method here. Okay, so we're making use of this method to get the total and to do these statistics on. All of these other methods don't really matter in this case. So it's a very simple calculator. We look at the bank account calculator, and we see that it's doing pretty much the same thing. So I've got a class called account calculator. I've got a running total, and I want to keep track of which account has the maximum value and which account has got the minimum value. And this in here is just exactly the same as the previous class. So I'm calculating the running total, and then I'm figuring out which account has got the minimum value and which account has got the maximum value. Okay, and the key method that I'm making use to do these calculations is account get balance. Okay, so it's very, very similar. I'm just getting the total from the cache box to do the calculations on that, and I'm getting the balance, the total balance from the account, from each account to do statistics on all of the accounts. And you notice that these two are very, very similar. So if you run this, it'll do the calculations correctly for the cache boxes, and if you run this, it'll do the calculations correctly for the bank accounts. So you notice that we're kind of it's a very common problem, and we're trying to solve it multiple times. So you can imagine many companies, many organizations trying to solve this same problem over and over and over again, which doesn't make sense. It makes sense to have a library or to have a class that just does this for anybody that wants to do it. And one way that you can do this is to make use of the capability of the interface. So we could keep providing specific calculator classes for any type that can be measured, or alternatively, ideally what we want to do is use a Mixin interface. So that's measurable classes, any measurable class, whether it's a cache box or it's a bank account, can implement the same method, get measure. So you can call this method anything that you want, but in this case we've called it getMeasure. And any class that wants to calculate itself, it needs to implement something called a measurable interface. Okay. So the first thing that you need to do is you need to define the measurable interface, and you need to define what it is you want to extract. What is that value that you want to extract from the cash box, from the account that is the common behavior. So you define your interface, public interface, measurable, and you define a method called getMeasure. So if I'm the cash box class, I need to implement measurable, okay, and I need to therefore implement this method. Yeah, so I say int getMeasure. Okay, so what value should I provide here for the cash box? What is it that I'm returning? Yeah, so it's the total for the box. What if it was the account get balance? So that's how it's done essentially. You define the interface, and then anybody who wants to be measurable, anybody that wants to acquire the behavior of being measurable, needs to implement that interface and needs to implement the method in however way that they want. And now, because I've done that, now I can create this measurable calculator. So it's exactly the same as the calculator for the cash box and exactly the same as the calculator for the accounts. So I just changed the naming. So instead of being called account calculator or cash box calculator, it's called measurable calculator. I want to calculate the running total, and I want to keep track of which of these measurable things has got the maximum value, which has got the minimum value. And the implementation is exactly the same. I calculate the running total, and I keep track of what's the minimum value and what's the maximum value. And all I'm doing all the time is I'm making use of this method called getMeasure, which has been implemented within the interface, rather than using the total for the cash box or using the get balance for the accounts. Yeah, so this is how you would implement it, for example, for the accounts. So you could do it within the account interface. You could do it within the abstract account. You can also do it within the lower level classes. So you can do it in the overdraft account, or you can do it within the free account. So it depends on where you think it's most useful to place this code. So in this case, we've implemented it within the abstract account. So all I have to do is add measurable here. So previously it only implemented account. Now it's implemented account, and it implements measurable. And I add this method in addition to the methods that I already have called getMeasure. And all I'm doing is I'm returning whatever this method gives, getBalance. Okay, so it's very simple. So now you can do something like this. You can say something like measurable. Sorry about my horrible handwriting. Measurable M is equal to new overdraft account, for example, or new free account. Okay, so now you can do that because you not only get the behavior of measurable, but you also acquire its type. So your overdraft account and your free accounts are not only accounts, but they're also measurable things. So that you can acquire that behavior as well. Yeah. So here we're just talking a little bit about where to do this. So do you want the abstract account to implement measurable, or do you want the free account or the overdraft account to extend measurable, or do you want your account itself to implement measurable? I mean, there's no right or wrong answer here. So it's entirely up to the organization how they want to do this. So it says here abstract account implements measurable is based on the assumption that all accounts are measurable. Okay, but you can also, within the hierarchy, you can create another type of abstract account that's not measurable if you don't want all your accounts to be measurable. So alternatively, the account interface could extend measurable, which means that all accounts will be measurable. And says here, be careful, because it means you've removed all kinds of flexibility. Basically, if you say that your interface extends measurable, it means that's it. It extends measurable, and there's nothing you can do about it afterwards. Whereas if you keep things at the lower level, at the implementation level, whether it's at the abstract account level or at the lower, more specific levels, then you've always got the option of creating a new implementation that is not measurable. Because remember, when you create an interface, you define its contract, you say that it's measurable, and you expose it to the outside world, you can't change it after that. You can only change the implementation unless you want to break everybody's code. Once you expose an interface to the outside world, people will start using it, and so you can't change it anymore. Otherwise, everybody's code would be screwed. You can't go in and change an interface. But you can always change the lower levels. You can create more abstract classes. You can always create more implementations. So it's always advisable that when you have this very specific behavior here, or something like that, is to keep it at the implementation level. This is how you would implement measurable for the cache box. So it's a lot simpler for the cache box. You've only got one class called cache box, and you just say it implements measurable, and then all you have to do is provide that method get measure, which returns the running total. So yeah, we end up with this overall class hierarchy. So we've got here, so this is our accounts, our bank accounts. So our account here, interface, I've got our abstract account, which implements the accounts, but it also implements measurable. Therefore, everything from abstract account downwards implements measurable, so it has that behavior of being measurable. But notice what we talked about before. This is our public interface, and it's not measurable. Therefore, I can, anytime that I want, create another abstract account, and I can create some other classes below that, and I can. So this implements that. And if I don't want it to be measurable, then I won't implement the measurable interface. I've retained that flexibility. So also our cache box implements measurable. Therefore, all of these abstract accounts and all cache boxes acquire the measurable behavior, and you can use it within the measurable calculator. So talk a little bit about polymorphism. In object-oriented programming, it means using the same name to refer to different implementations of a method. Okay, so that's the main meaning. So we're talking about method overloading, and we're talking about method overriding, which we already talked about. But it also means multiple implementations of the same interface. So you have a single interface, and you have multiple different implementations. That also is polymorphism. For method overriding, and for interface implementation, the method to execute is resolved dynamically at runtime. So it depends on the type of the object. So that's something we've talked about over and over and over again. So which method gets implemented depends on the type of the object. So always remember that. So using interfaces plus polymorphism gives us this feature, this implementation independence, which is very, very useful. So an interface reference can refer to any object that implements the interface. So now, because we're implementing measurable, you can do this. You can say measurable m. So if you just say measurable m, obviously m initially points to null. It's not pointing to anything. But then after that, you can do this. You can say m is equal to new free account, for example, or you can say m is equal to new cache box. So you've got. So the reference type is measurable, but the object type is free account, and then it's cache box. So always remember there's a difference between the reference type and the object type. You cannot construct an interface, obviously, so you can't do this. You can't say m is equal to new measurable, okay, because measurable is just an interface. And you can call any of the interface methods. So you can say. So in this case, there's only one method, which is getMeasure. So you can say m.getMeasure, but you can't call any of the other methods. So in this case, I can say m.getMeasure, but I can't say, for example, m_total for the cache box, or I can't say m_getBalance for the free account, or m_withdraw, or m_transfer. I can't do any of those things, because at the moment, my reference type is measurable. Yeah, there's a question which says, which method is called at runtime. The question is asking at runtime, which method is called in this case, looking at the code preceding that. The latest assignment for m is new cache box. So it will go down to the cache box object and at runtime, and it will run the method within cache box. So it'll return the total within the cache box. So yeah, so polymorphism means that you execute different versions of a method through the same interface. The method that is executed depends on the referenced object, and the type of the object determines which method is called. So abstract account.getMeasure is executed if M refers to a free account, and cashbox get measure if M refers to the cashbox. So so both get measure methods are versions of the measurable.get measure. So this dynamic runtime resolution is called late binding. So this is kind of a summary, or reference type versus object type. So what you do depends on the type of the reference object. What you can do depends on the reference. What gets done depends on the type of the referenced object. So when you say measurable M is equal to new cashbox, this is what you can do. Okay, you can call get measure, but you can't call any other method. It's the same here as well. So if you want to make use of any other methods within cashbox or within free account, so if I want to make use of the other methods within free account or cashbox, so you have to cast it down. So here's an example of how you do that. So casting changes what can be done, not how it gets done. So how something gets done, remember, is resolved dynamically at runtime. But what gets done is determined at compile time. So if I want to tell the compiler I want to do these things, and it's okay to do these things, then you need to cast within the code. So you do something like this: cashbox C is equal to M casted to cashbox. Okay, and the same for account. A is M casted to account. And remember that when you do casting, to check the instance first. So obviously only do this if you're sure that M contains an account, and only do this if you're sure that M contains a cashbox. So now that you've done the casting with using C, you can now access any of these methods: get measure, total, empty, pay, and the other pay as well. And with A, you can access these methods, which are deposit, get account number, get balance, transfer balance, and withdraw. So previously, when we called it free account, we had access to get measure, but now it's disappeared because get measure is placed in the abstract account, and here I'm casting to account. I'm not casting to the abstract account. If you want to retain the get measure method, so you need to cast to the specific type that you want. So you need to cast to either free account or you need to cast to the overdraft account. So this brings us to this slide here. So what is the main problem with mixins? So if we go back to the relevant example, so you had to, so within your abstract account or within your cashbox, you had to, that particular class, for example, the cashbox had to implement measurable, and you had to add this method. And what does that mean? It means that you need to be able to change the code, and therefore you need to own that class. It needs to be one of your classes. It needs to be part of your own libraries to be able to change the code of a particular class. If, on the other hand, you're working with somebody else's code, let's say there's a useful class that already exists in the Java library. So those classes are not owned by you. You can't change them. You can only use them. Okay, so you can't actually, if I've got a class within the Java library that I want to measure, I can't do that. I can't take that class and say that it implements measurable and add an extra method in there to get that data. So we need another way in order to be able to do that. So mixins aren't always possible. So we use another technique. We have another technique available to us as well. So mixins are a common and useful pattern, but you have to modify a class to implement the mixin interface. This is good for new classes or existing classes that you control. So that's the key thing. You need to be able to control the class to apply the mixin design pattern. But it's not so good for classes you don't control. So the problem is, how do you get the desired behavior provided by mixin without modifying a class? So the solution is to use something called a strategy design pattern. You implement a strategy interface rather than a mixin interface. You decouple the measurement from the object to measure. So the class itself can't measure itself. So if I don't own a class, I can't implement the measurable interface. I can't add a method for that class to be able to measure itself. So what I have to do is to bring another class to measure it. Okay, so you're going from creating a measurable interface, therefore, to a measurer interface, because if there's something I don't control, I need to try and measure it externally from the outside. So instead of implementing a measurable interface, we implement a measurer. So it looks very similar to the measurable interface, except that it takes not only so the method that you add to it takes not only the data you want to measure, but it needs to take the entire object, because you need to be able to manipulate the entire object to get that data you want to measure. So we implement a measurer to measure objects, as opposed to requiring the objects to measure themselves. Okay, so that's the general principle or general idea behind the strategy design pattern. So this is basically what you do. So here's my Cashbox class, here's my account interface, and what you do is you create a measurer class. So this is my strategy design pattern. I have to create a new class that measures my class, and then it's this additional class which implements the measurer interface. Okay, so you need to have this additional level of complexity. There's no way around it. So it's obviously having the measurable interface using Mixin is a lot simpler, because classes can measure themselves. You can modify their behavior to do what you want. But if you can't modify the behavior of a class, you need to add some complexity to be able to get any data that you want. So this is the level of complexity. You have to add you have to add a new class that does the measuring, and it implements this measurer interface, and then your statistics class can do any statistics it needs on those objects. So by doing this, the classes interfaces of objects to be measured, account and Cashbox, are completely decoupled from the measurer interface and from the calculator. The measurer implementation, account measurer, and Cashbox measurer determine how an object is measured. So this is just repeating the slide of the Mixin design pattern, just to show you the difference. So whereas previously your bank account implemented the measurable interface directly, when you're using the strategy design pattern, so you have to create this additional level of complexity in order to be able to do any operations that you want to do. So Mixins and strategies both have their place. They're both very useful. The problem is, as we said, not all classes can implement or be retrofitted with a Mixin. But also not all classes will expose sufficient information to apply a strategy. So you still, so when you don't control a class, you're still hoping that there's a method in there that's going to return the data that you want. Whether it's, so in the Cashbox, it's the total amount in the Cashbox, or in the bank account, it's the total amount of money in the bank account. So you're hoping still that there's a method that's going to return that information for you. But not all classes will do that. Some classes are not going to return anything at all. So in that case, you can't apply a strategy, or you can't apply a Mixin. So you just can't do anything with those classes. Yeah, so there may not be a public method that can be used to measure an object, in which case. So the Java collections framework use both for sorting. So one of the things that you might want to do with objects is be able to sort them, and a popular method that you can use, popular interface that you can use in order to sort objects from within the Java API is the comparable and the comparator interfaces. So you can use either one of them depending on whether you own the objects or you don't own the objects. So if you own the objects and you have full control of them, they're your objects, then it makes sense to use the comparable interface, which is a Mixin interface. You simply say my class implements comparable, and you implement whatever method is required. But if you don't control the objects, then the API provides you with an interface to use the strategy design pattern. So there's a comparator. So interfaces versus abstract classes. So interfaces and abstract classes both define a type that allows multiple implementations. Abstract classes can also provide an implementation, so interfaces cannot. So remember that interfaces, you can't include implementation within the definition. So the interface definition should only contain what methods you want implemented. Implementations of the type defined by an abstract class must subclass the abstract class. So we use implementation inheritance there. Any class anywhere in the hierarchy can implement one or more interfaces. So that's the Mixin idea. Unlike plain old traditional inheritance, you can only extend one class at a time, but with interfaces you can implement more than one interface. Interfaces provide looser coupling and less brittle code. Declare an interface for any publicly exposed type. So if you have a publicly exposed type, it makes sense. You should always create an interface for that. Refer to objects by their interfaces whenever possible. So that's Joshua Block's item 52 if you want more information on why that is. Program through interfaces and only use or cast to implementation when absolutely necessary. So that goes back to our bank account example where we had the transfer balance, was it, or the withdraw method, where we noticed that by not programming to the interface, we ended up with a logical error. Use interfaces only to define type. Do not use interfaces just to declare constants. So one thing that you can do is declare constants in interfaces, and that's not regarded as good practice. So you want to keep the interface just as an interface, just to define what can be done with this hierarchy. You don't actually include any data in there. So if you want to create constants, associate constants with a type, or use a non-instantiable utility class to do that. So usually interfaces and abstract classes work well together because you want a place to put the common code in, which is what the abstract class is. But generally, if you don't have any common code, then prefer interfaces to abstract classes. So the advantage of that is you can retrofit existing classes to implement a new interface without damaging the type hierarchy. Again, the same advantages of using interfaces. And the same is not true for existing classes extending a new abstract class. Interfaces can be used to define mixins. They support non-hierarchical frameworks. They allow safe enhancements. Abstract classes enforce inheritance. And when possible, so you want them to work together, provide an abstract implementation of any non-trivial interface. If it's something very simple, then sometimes you don't need an abstract class. You don't have that many concrete types of implementations. You might have only one or two. Then you don't need an abstract class. But if it has any level of degree of complexity, then you want to have an abstract implementation. Almost no downsides to using interfaces, but be aware. Finding a top-level interface declares the type to be part of your publicly accessible API. So the interface is the public-facing part of your code. So that's what the developers and users will look at first of all. So it's possible to have a private or protected. It is possible to have private or protected interfaces, but only when nested within a class. So you can do that if you want. If you've got some kind of a structure that you don't want to be publicly exposed. So you can add default methods to your. So if you absolutely have to extend the functionality of your interface, nowadays you can do that. You add these default methods, and the rule is that existing software that's used your interface does not have to implement those default methods, so it won't break their code. But then you don't have a contract anymore. Okay, if you create an interface with default methods, then you're not enforcing this behavior on the people that you use in your classes. So it's not really an interface then. It's just a way to extend your code without breaking other people's code. So you only want to use that absolutely when you have to. But the general idea of having interfaces is to have this contract. So in general, if implemented correctly, it's impossible to modify an interface without breaking all existing programs that use the interface. Implementations of the previous version of the interface do not, by definition, implement the new modified version. In contrast, it is possible to evolve classes, including abstract classes, without breaking existing code. So these dependencies are not a problem during the initial development of code, obviously. So we're talking about post-production. So when not to define an interface, so do not define a top-level interface for a type that's not intended to be public. It is possible to subsequently extract an interface. So IDEs provide refactoring support for this. So for example, one of the things that you can do is you can extract an interface, so it'll automatically rewrite some of the code for you so that the other classes are not dependent on the interface, so remove the implements keyword from all the remaining classes. So refactoring is just it's another word for automation. So if you change the name of a class, you don't have to go ahead and manually change everywhere that you've used that class by hand. So there's a refactoring menu item within the Eclipse IDE. So have a look at it and see the different things that you can do. It is not necessary to define an interface for a public type that will not be or unlikely to be extended. Okay, so an interface is usually intended to be extended by concrete classes. But if you've created an interface and it's unlikely that anybody's going to want to implement that interface, then I guess there's no point in creating that interface in the first place. In this case, prevent inheritance and just create a simple class that'll do the simple tasks that you want to do. Again, if you change your mind, it's possible to refactor and extract the interface for the type. But this is just during production time. Once you've released it to the public, then that's it.